And we see the data appear right there. Across the axis at the top, the horizontal axis, that's array distance down the recording refraction microtremor array. From the top to the bottom is 30 seconds, and you also get your amplitude color bar. We're seeing the waves come in, and these chevrons are formed every time a wave is generated, maybe by traffic. Being a very quiet site, we wanted to generate a little extra noise by driving. Now, that's just the first record, okay? There are 28 records here, and if we scroll horizontally at the top here, you can see all the different records. And what we're mainly looking for is to make sure that all the geophones stayed plugged in for all the records, and that there isn't some unusual event that's special to one record. That would be something to watch out for later. Okay, the data look very good. So we're going to go ahead and do a little pre-processing. So you find that under the Methods menu, and you go to on each vector, and first an amplitude mean removal, which I call centering. And so then you hit the CTR button to complete that. All right, and let's look at the records again. Okay, things are a little bit more even, which is good. And then under Methods, on each vector, again near the top, the trace equalization gain, TE gain, we press that and press the TE gain button. And now the records are fully ready for processing. Some of these records are, maybe have more or less traffic noise than others. We may see the results. Okay, so now for the trademarked REMI processing. So we go to on each plane, and we invoke the ViaSurf REMI method, which you can also get with a keyboard shortcut of Control-R. Now we confirm the information for the analysis. We're going to employ a maximum frequency of 50 Hertz, and we're going to look down to a minimum shear wave velocity of 650 feet per second. And that's fine for a general minimum possible shear wave velocity. Now, if this was a swampy site, or we knew it was a very soft site, we might reset that to be only 300 feet per second. Or for those of you overseas, we generally use a default minimum velocity of 200 meters per second. And if it's a swampy site, then we'll look down around 100 meters per second. And you can change, which one you're going to analyze. So you can do projects in either feet or meters. Okay, and now we're going to use, we're assuming this is a straight line with even spacing of geophones, not some special project for which we'd have to put in the actual 3D offsets of all the geophones. All right, and so our sensor spacing, our geophone spacing was 8 meters. We could put in what it is in feet if we wanted to. And there are some special methods that we can invoke for those difficult data sets that sometimes crop up. But I want to remind you, you can always call us, because we are your geophysical division, and we will help you if there's any trouble with the standard processing. So then we go ahead and hit the ViaSurf REMI button. And it takes just a moment to run through each of the 28 and do the calculation. Okay, now what I'm seeing here, especially if I again run through the result of each of the of each of the records is that I didn't set the minimum velocity low enough. So I need to set the minimum velocity lower to make sure I have a blue area on the left. So I'm just going to cancel out of that and go ahead and redo the analysis. Invoke the ViaSurf-ReMi method. It remembers everything I set before, and I'm going to go ahead and set that 300 foot per second minimum shear velocity. And maybe I'll reset it to a maximum of 40 hertz. And then hit the ReMi ViaSurf button again. Now we're starting to see a dispersion curve. What are we looking at here? Velocity increases to the right. Frequency increases up. The higher frequency, shorter wavelength waves are sampling shallower in the subsurface. The lower frequency, long wavelength waves are sampling deeper. So the frequencies we see at the top, those are for the shallow part, and down below, that's the deep part. And that's the orientation that we're looking at here. Now, if we go through and scroll through these different records and their analyses, we can see that we have a consistent dispersion curve despite the various artifacts of the non-Rayleigh wave part of the wave field. So, and each of these records is, they do have variable quality, but they're all good enough to include in our analysis. So what we're going to do now is we're going to combine the dispersion signal from all the records. Okay, and so we go to on each plane and we flatten it all down together. Okay, and you can just pick the flatten button here and push that. So there's the result of putting all the records together. All right, so now we're going to pick the dispersion curve. Now, which way should a dispersion curve go? The first thing I'm going to do is I'm going to view this. I'm going to zoom it to 200%, just to see things a little bit better. And what am I looking for here? Well, at most sites, not all, but most sites, at the very top, in the shallowest soil, the shear velocity will be low. The soil's loose. And then as you go down in depth, it'll get more compacted and the shear velocity will rise. So we should have a down to the right kind of curve, and that's what we're looking at here. That's what we're focused on. These ones that go up to the right, those are just artifacts of the processing, and we can safely ignore them. So now, knowing that we're looking for this down to the right curve, we want to be on the left side of it. We want to be where these blue areas end to the right, and we're going to pick the last blue dot that's just to the left of a slightly yellow dot. And that's going to form our dispersion curve. Okay? Now, let's pick the easy ones first. Okay? So here about in the middle, that's the rightmost blue before it gets yellow. And I don't have to pick every square. I can just pick several. Okay, and I can keep going, and I want to go to the right. All right, so I think, past this artifact right there, we get to that blue dot there. All right, and then now I'm going to start picking every single one. And actually, I'm going to blow this up a little bit more. I'm going to view it and zoom it to 500%. Okay, and now I'm going to scroll down to look at the bottom part of the curve. So we're picking every one, and we're picking the blue that is just to the left of the yellow. And so I just can keep doing that. Yeah, I think that one is slightly bluer. Okay, that's the blue one. Now the blue one's down here. And we go further. These are the easy ones to pick. Okay, and let me just scroll up. Right, we're picking on the right side of the blue. Okay, maybe I can pick a couple more here. Maybe there. Okay, just to have a few more. Of course, we don't have the same confidence in the picks that are in a big yellow area compared to the confidence we have in the picks that are on the right side of the blue area. All right, so that's a basic set of picks. Do I want to even do one more? Maybe I would do one more. Okay, I do have less confidence in that pick than in others. So now we have our basic set of picks. I'm going to go back and view it at 200%, just so I can see it all on the screen at the same time. And now, to have this included in the final report, what I need to do is File and Save JRGPAC. That's our internal data format, and I'll just save it right there, and the suggested name is just fine. Okay, so now we've saved the JRGPAC. One more thing we want to do is we want to have an image of this dispersion with the picks on it, just to be able to prove to, for instance, the building authority that we've collected good data and that we can prove it and we've picked it correctly. So this remains in your report as a record of the quality of the data that you got and the quality of the result you turned into your client. So that we get, again, from the File menu, we save an image and we write a PNG file. You can certainly write a JPEG if you want. And again, the default name is just fine. Okay. So now we're ready to put 1DS aside for a little bit, and we're going to start up the other module, the DISPER module.